Allora, buon pomeriggio. Good afternoon. It's my pleasure to be here today to talk about the management of river systems and the evolution of new thinking, new perspectives, and in particular the importance of a geomorphic perspective in the larger scale management of river basins. I will be speaking of this issue by presenting first the context of river basin management globally, and then specifically looking at what it is that a geomorphic perspective has to offer, what it brings to us, what it gives us in terms of the ability to provide direction to management, managers and decision makers, and in essence why we should consider this as being part of the way we approach river systems and some of the tools and new developments and strategies that are accompanying this. So that's the general outline for where we're going today. But to start, I want to have us first step back, way back, with this satellite view of the Earth at night, taken 20 years ago. Now the Earth would even look different. But the reason this slide is in here is to remind us of where it is that people live and where it is that people, the river basins that are being so heavily managed these days are located on the planet. And what you see when you look at this image of the Earth at night is that the population centers that the places that are lit up are the developed and developing world both, with a high concentration of people in Asia, in India, in China, and that these are in fact where the major river systems of the world and the major population centers of the world coexist. So if we look at the 10 largest river basins in terms of their size and also in terms of their population, we see that roughly 30% of the world's population currently lives in these 10 largest river basins. Right now, 10% of the total gross domestic product, or 25% of the total gross domestic product will be from this population by the year 2050. So these are centers of population, these are centers of economic growth and potential, and it is for these reasons that river basin management has such an acute and important place or should have such an important place in our thinking. So I don't need to belabor the point of what rivers are used for. They include a variety of objectives and goals and human needs, everything from irrigation to agricultural withdrawals irrigation, agricultural withdrawals to municipal water, water for industry, water for hydropower, and what these give us, of course, along with other direct resource extraction in the form of things like gravel, and also the newly emerged objective of restoring rivers for a variety of purposes, including endangered species, water quality, and even just the aesthetics of large rivers. All of this gives us a competing set of objectives for rivers, a large and competing set. And it's for these reasons that river basin management is so complex. As a result of these varying objectives, the world's rivers are highly managed, highly modified. A paper about 10 years ago by Nielsen and colleagues in Science identified the global range of modification, and most of this modification is due to interventions such as dams that are specifically designed to modify flow sediment regimes and provide power for populations. So these dams are distributed worldwide. there is no portion of the world that is not highly modified. And what this means is that finding a river that has not been affected by human activities is extremely rare. Another challenge that results from this overlay of objectives and populations is degraded water quality. And again, this is not just a problem of the developing world. This is a developed world problem. And we see it emerging in places like the United States, like Europe, like China. Water scarcity, the inequality between the demand for water and its availability is similarly a global problem. And so the river systems of the world are faced with these ranges of challenges, and it's likely that these will only become more acute, more pronounced, as the climate changes in the years to come. So we're faced with a situation where there are many people sitting at the table, all having legitimate claims on the river, its water, its power, and its geography. So all of this suggests that we should be looking for ways to develop integrated approaches to river management. And in fact, we do have emerging directives on a global scale from around the world that in fact call for this sort of integration, whether it is the Water Framework Directive in the European Union, whether it is the Clean Water Act and related legislation in the United States, whether it's directions for integrated river management out of India, and there are other examples even in throughout the world that of this sort of direction. Yet despite these directives which call for river basins to be managed with an integrated framework, we have very few good examples of where this sort of strategy, this sort of integrated strategy, has actually been achieved. Why not? Why has it been so hard? Well, the simplest answer is it's complicated. That is, as I've indicated, because of the multiple objectives, competing objectives for river systems, because many of these objectives involve trade-offs between various ways that rivers are managed, because the fundamental issues of river management run very quickly into issues of political power and social equity. All of these make the integrated management of river systems and corresponding resources rather complicated. But my focal point for the remainder of the talk is not these, but rather an additional factor which I think contributes to difficulty in managing rivers in this integrated fashion. And it's a lack of what I will call landscape or geomorphic perspective for river management. It's really that which I will argue is what is needed, that what we should be orienting ourselves for, and something that we can actually, I think, affect rather more directly than some of those other causes, is bringing to bear what we understand, what we know about landscapes and rivers to bear on the problem of river management. What do I mean by a geomorphic perspective? Briefly, a geomorphic perspective places human activities within a geological context by reading the landscape in terms of both the deep and recent geological history, the dominant processes, the primary landforms, and the interactions among the history, the landforms, and the processes, all with an eye to providing guidance for human action. So that's what I mean by a geomorphic perspective. It brings our understanding of underlying process and form directly to bear on the problem of an integrated approach to river management. Why do we need such a perspective? Well, it's easy to point to examples where the absence of such a perspective causes problems, and these are well known within the engineering, geological engineering community, of course. Here's an example from the northwest of the Pacific Northwest of the United States, where a river has been confined and straightened only to reassert its tendency towards meandering by overtopping and breaking out of its levee system. Another well-researched, well-understood example was the tragedy of the landslide at Vajon in the Italian Alps, where the failure to recognize a large, deep-seated landslide complex accompanied by the construction of a very large dam at the base of this landslide resulted in a slope instability, producing effectively a tsunami that overtopped the dam, ran down a very narrow gorge, ran across a large river valley, and destroyed the town of Longarno and many thousands of people. This is a disaster of large proportions that's pointed to in the engineering geology community as an example of the importance of understanding the deeper roots. A similar example comes from Vargas, Venezuela, the Vargas debris flow several decades ago, which again killed many thousands of people because the town, a very highly dense populated town, had been sited on an alluvial fan and was therefore subject to being inundated by debris flows. So these are obvious examples where understanding the landscape is clearly an important component of managing river systems and their various pieces. But there are some less obvious examples as well. For example, recent work by Kondoff and others points out how the development of large river basins, for example, the progressive damming of the Mekong River in Southeast Asia has resulted and will continue to result in sediment starvation downstream. So the numbers on this graph indicate cumulative sediment starvation at present, and if the entire complex of dams is built into the future. And so this is a kind of cumulative effect of management that is affecting fundamental fluxes of material such as sediment through large river systems. Another less obvious example is the consequence of deforestation, perhaps the best example of this being in New Zealand, where a history of land clearance and burning, the introduction of sheep, and that accompanied the European settlement of this area, resulted in massive reactivation of large, deep-seated slide complexes and associated sedimentation problems throughout the rivers of New Zealand. An example drawn from my region in the Pacific Northwest is the decline of a native species, the salmon populations of the rivers of the Northwest, which are responding to a plethora of forcings by increased the presence of dams for hydropower, the presence of hatcheries contributing reducing genetic diversity, the presence of habitat modifications, the large-scale increase in harvest over recent years, and other factors, all are cumulatively affecting this both economic and really a kind of symbolic resource of the region. So all these become so these examples, these less obvious examples again, underscore a rationale for bringing a broader scale landscape or geomorphic perspective to bear on our management of river systems. So in the remainder of the talk, I'm going to talk specifically about what the elements of this sort of perspective might be across a range of scales, ranging from the site-specific all the way up to the basin. And I'll also be emphasizing some of the tools and new emerging tools that we have at our disposal that I think helps us achieve this sort of perspective. So starting at the site level with perhaps what might be the most obvious places where a geomorphic perspective can be implemented. We have examples, for example, the recent landslide in the Pacific Northwest, the Oso landslide that is the largest historic landslide in U.S. history, killed 43 people, because it was not evident that a town had been sited directly across from large, deep-seated landslides that had failed in the historical past. The presence and the emergence of LIDAR as a tool has allowed us now to not only identify these features, but also begin to date them as well, so that these new imaging techniques give us an ability to actually begin to cast processes such as large deep landslides here in glacial fluvial till in their place them into a historical and geological context to inform things like the siting and development of cities. Other examples can also be pointed to across a perspective that might be seen as a longitudinal perspective as we move down river systems. In the upstream most reaches, the ability to identify places, parts of the landscape that are prone to alluviation or alluvial inundation or debris flows is increasing rapidly. And here again, a variety of new techniques are at our disposal, and these include the ability, of course, to field map, which has been with us for a while, but now the emergence of both LIDAR as a way of identifying where historically debris flows and their features are present on the landscape. And secondly, the emergence over the last 20 to 30 years of numerical models that give us some predictive power in terms of predicting where debris flows are likely to go. So here are some tools. Here's a piece of the landscape where at a site level where this geomorphic perspective can be implemented. Another example from further on downstream in the river system, is recognizing what I will call the inevitability of some geomorphic processes such as floods and designing accordingly. Here an example from Switzerland where river engineers have designed a fluvial accommodation space to, in essence, decant floodwaters before they affect population centers. So this recognition of geomorphic processes, of course, such as floods, but also then designing and building schemes into the management of these rivers to accommodate this, I think is another example of this sort of thinking at a site level. But we can also stand back and look at a river basin level as well. Here's an example, again from the Pacific Northwest, where the historical geomorphic behavior of the river, in this case the Willamette River in Oregon, has been interpreted. Shown in the panels on the left, on the far left, is the historical channel pattern of the river and its distinctive braid and bar complexes that existed as recently as about 150 years ago. And to the right is the modern river, which has been constrained by a variety of erosion control measures and such. What we can do, however, because of our ability to look into the past and interpret and see this history, is to begin to identify parts of the river system which have historically had the potential to wander and migrate laterally. And as suggested in the lower right panel, where such free meander zones or free braiding zones do not coincide with high demographic or sociological pressures, we can identify portions of the river system where potentially erosion control measures could be relaxed so as to accommodate and restore, in a sense, this suite of natural processes back into the landscape for a variety of purposes, which can include ecological benefits, temperature benefits, water quality benefits, and the like. So what we are now being able to do because of this ability to interpret the past and bring it to bear on the present is provide guidance for where restoration strategies could be implemented. More on this in a few minutes. Another example This was some work that we did about a decade ago, but the essential, the essence of this work was to recognize that dams are not created equally and do not do the same things to rivers, in the sense that dams affect both the flow regimes and the sediment transport regimes, with most dams affecting capturing sediment, but not all dams affecting the hydrology. And so what we have in the graph are essentially, without going into the details here, two-dimensionless numbers that are essentially the relationship between the degree to which the dam has affected the sediment transport capacity of the river, shown on the x-axis, and on the y-axis, the degree to which a new sediment is being resupplied to the river downstream of the dam. And depending on where and how a dam fits into this geomorphic scheme defines whether, in fact, the bed below the dam will be subjected to aggradation or degradation, and that individual rivers will, in fact, experience trajectories of change as the water flows downstream from the dam. So the point here is that this kind of thinking is giving us a way of looking at dams in their geomorphic context, recognizing differences among dams, and ultimately some degree of predictive power in terms of being able to, in advance of dam construction, actually predict what the direction of geomorphic change is likely to be. So that's another example. A third example that's stepping back all the way back to the basin scale is the ability now to develop regional models that show regional patterns of geomorphically relevant processes such as bedload transport. Here's some work by my colleague Jim O'Connor and his team at the U.S. Geological Survey, who have used simple models of sediment transport coupled with sediment supply to begin to build predictive schemes showing annual fluxes of bedload at the scale of an entire region, where the thickness of the line, the blue line, represents the volume of sediment of bedload that's in flux. And so with these sorts of simple models applied at the regional scale, we can begin to make predictions and to actually guide managers with respect to issues such as how much gravel can be extracted from a river system without causing further degradation. Where are the best places to locate resource extraction? So again, guidance for river management is a clear outcome of these sorts of perspectives. Finally, I want to focus on what I see as some very useful emerging trends in overarching and overall river basin interpretation and management. And these are frameworks. These are essentially geomorphic frameworks which have been advanced in the recent past, in the last 10 years. Perhaps one of the most well-developed examples is the work of Gary Brierley and Kristen Friars in Australia with their river styles framework, which is explicitly directed at what they call, quote, reading the landscape, unquote. And this scheme is essentially a guidance. It's not a cookbook, but it's a guidance for managers that is in which several distinctive components are identified. The characterization, first, the characterization of the geomorphic condition of the river system at present. Secondly, an interpretation of the river's history, bringing to bear the kinds of historical data that I showed previously. Third, the prediction and the identification of river trajectories that might move out into the future and how these are spatially distributed timescales of evolution of the river system itself. And finally, bringing this all together into management directives and guidance that take advantage and account of these various processes. Here in Italy, the same sort of large-scale river type framework has been developed by Massimo Rinaldi, Martina Busattini, Nicolas Ryan, Francesco Comiti, and colleagues in the EDRAME framework. And again, this draws on some of the same schemes that have been advanced by the River Styles direction, but have some of the same elements, the recognition of the importance of varying scales, everything from the individual channel unit all the way up to the basin. The recognition of the importance of identifying and characterizing the channel condition, identifying the historical patterns and trends in the system, identifying future trends, and using all of this to provide management guidance. Here's an example of this sort of guidance and this sort of interpretation from the River Magra system. And so what is shown here in the colored bands at the bottom are degrees of change that have been expressed by various processes, including the construction of dams, the afforestation of the uplands, gravel extraction from the river system, and direct river modification. So these bands represent a time series of historical interventions in the river. At the top of the graph is the response of the river system over time, both in terms of its width, shown in blue, and its bed elevation, shown in red. And so basically what Rinaldi and colleagues have shown, and Sarayan and colleagues have shown very clearly, is how over time, because of these cumulative effects of these multiple forcings, the river systems have both incised and narrowed. So with this sort of perspective in mind, we can identify, we can diagnose, we can begin to implement changes to rivers that accommodate where they've been in the past and where they might be going into the future. So the idea of reading the landscape is more than just a simple phrase. It's a set of concrete, rigorous, and sequential actions that give us the advantage of the tools of geomorphology, the perspectives of geomorphology, and bring them to bear in a way that can be used for a variety of purposes, whether it's the restoration of rivers, whether it's guidance as where to site a new development on rivers such as dams or erosion control, and that these new frameworks are then directly helping us implement this sort of scheme. So, what I want to leave you with is this idea that a geomorphic perspective for managing river systems is fundamentally a useful concept, and it's emerging as a way, first, of putting human activities and harmonizing human activities with the landscape and river system as a whole. It provides a way of bringing history to bear on our present understanding and our future direction for river systems. It clearly can be implemented at a variety of scales, and it's being supported by a variety of new tools and new developments that are helping us then bring and further this perspective in our global challenge to manage the world's rivers in ways that can accommodate an ever-increasing population and a changing environment. So with that, I thank you for your attention.